We hear this sound in war films and documentaries, but we stopped paying attention to it long ago. The rumble of tracks grinding over broken ground, the hydraulic whine of a turret rotating, the crack of a main gun firing. And yet, inside a tank, real mechanical violence is happening every single second. Dozens of tons of steel are moving across terrain that would destroy a wheeled vehicle, while hydraulic systems operate under pressures exceeding 300 bar, and a crew works in a sealed compartment where a single armor penetration can mean catastrophic failure. If you enjoy understanding how machines really work, stay here. The key thing to understand is this: a tank is not a regular vehicle. Its job is not to transport cargo or personnel from point A to point B, but to deliver firepower while surviving direct attack. In reality, it is a mobile weapons platform that happens to move. That's why tanks differ so dramatically from any other military or civilian vehicle in design, in operating loads, and in the level of engineering involved. The first tanks appeared during World War I, when armies faced a simple problem. Troops could not cross open ground under machine gun fire. Engineers quickly realized that armor alone wasn't enough. The machine had to move across trenches and barbed wire while delivering suppressive fire. That led to the first primitive tracked vehicles. Over time, they evolved into complex weapon systems built around three competing demands: firepower, protection, and mobility. Engineers call this the iron triangle. You can never maximize all three at once. All of a tank's power starts with the engine, but the engine does not drive the tracks directly. The critical component here is the transmission. A tank transmission is nothing like what you'd find in a truck or car. It must handle extreme torque at low speeds, provide precise steering control, and operate reliably under combat loads that would destroy civilian gearboxes in minutes. That's why tank transmissions use planetary gear sets and hydraulic actuators instead of conventional designs. The transmission diverts power to the final drives, which turn the drive sprockets that move the tracks. But the engine has another job. It must also power the turret traverse system, the gun stabilization hydraulics, the electrical systems, and the fire control computers. All of this happens simultaneously. That's where hydraulics take over. High-pressure hydraulic pumps push oil through control valves and into cylinders that move the turret, elevate the gun, and keep the weapon stable. This oil is the machine's lifeblood. Without it, the entire steel structure instantly becomes dead weight. Now, let's talk about what makes a tank a tank. The main gun. A modern 120 millimeter smoothbore cannon can fire a kinetic energy penetrator at over 1,700 meters per second. That's 5 times the speed of sound. The projectile weighs several kilograms and carries enough energy to penetrate hundreds of millimeters of hardened steel. But here's the problem. The tank is moving. The ground is uneven. The target might be several kilometers away and also moving. Engineers solve this with gyroscopic stabilization. Sensors detect every movement of the hull, pitch, roll, yaw, and feed that data to a fire control computer. The computer calculates corrections in milliseconds and sends commands to hydraulic actuators that adjust the gun's elevation and traverse independently of the hull's motion. This system compensates so effectively that a tank can fire accurately while moving at 40 kilometers per hour over broken terrain. The gunner sees a stable sight picture even as the entire platform pitches beneath him. Then there's recoil. When a 120 millimeter gun fires, it generates a rearward force exceeding 50 tons. If that force transferred directly to the turret structure, it would damage the mounting and injure the crew. That's why the gun sits in a hydropneumatic recoil system. 2 cylinders, one filled with hydraulic oil, one with compressed nitrogen, absorb the recoil energy over a controlled distance. The gun slides backward roughly half a meter, the energy dissipates, and springs return the gun to battery. The entire cycle takes less than a second. Inside a tank, ammunition is stored in compartments separated from the crew by armored blast doors. In the M1 Abrams, rounds sit in a bustle at the rear of the turret with blowout panels designed to vent explosions upward and outward. If an enemy penetrator breaches the armor and ignites the ammunition, the force vents away from the crew compartment instead of incinerating everyone inside. This design saves lives, but it doesn't eliminate the danger. A direct hit to hull ammunition storage can still cause catastrophic internal detonation. The suspension system is equally critical. A tank weighs 60 to 70 tons and must cross terrain that would immobilize any wheeled vehicle. Modern tanks use torsion bar suspension or advanced high-drop pneumatic systems. Each road wheel connects to a spring steel torsion bar that twists to absorb impacts from rocks, ditches, and debris. High-drop pneumatic systems go further, using pressurized nitrogen and hydraulic oil to actively adjust ride height and lean angle. This allows the tank to tilt forward when firing from a hull-down position or squat to reduce its silhouette. Track tension must be precise. Too loose, and the track throws off the drive sprocket during a hard turn, immobilizing the vehicle. Too tight, and the connecting pins shear under load. Crews adjust tension manually in the field using specialized tools. It's one of the most common maintenance tasks, and getting it wrong can strand a multi-million-dollar machine in hostile territory. Inside a tank, there's more than just steel and ammunition. Its most dangerous enemy is what can penetrate the armor. The most common threat is the shaped charge warhead, used in rocket-propelled grenades and anti-tank guided missiles. When a shaped charge detonates, it collapses a copper liner into a superheated jet traveling at several kilometers per second. This jet can penetrate over 600 millimeters of rolled homogeneous armor. Against this, passive steel armor is completely insufficient. That's why modern tanks use composite armor. The hull and turret are layered with ceramics, hardened steel plates, and in some cases depleted uranium mesh. These materials disrupt the jet's formation, causing it to disperse before reaching the crew compartment, but even composite armor has limits. Top attack munitions, missiles that strike the thinner roof armor, remain a lethal threat. Engineers developed reactive armor as an additional layer of protection. Explosive reactive armor, or ERA, consists of metal plates with explosives sandwiched between them. When an incoming shaped charged jet hits the ERA block, the explosives detonate outward, disrupting the jet before it can penetrate the main armor. ERA is effective, but it's a one-time defense. Once a block detonates, that section is unprotected until the crew replaces it. Inside the crew compartment, fire is the most immediate danger after a penetration. A breach can ignite hydraulic fluid, ammunition propellant, or fuel. Modern tanks are equipped with automatic fire suppression systems that detect temperature spikes or open flames and discharge halon gas in under 100 milliseconds. The system floods the compartment, displacing oxygen and extinguishing the fire before it spreads to critical systems. Without this, crew survival rates drop catastrophically. But chemistry isn't the only threat. Escape from a damaged tank is not guaranteed. Hatches are heavy and require significant force to open from inside. In combat, external threats, small arms fire, artillery, or enemy infantry can make exiting the vehicle impossible. Crews train for this scenario, but the reality is brutal. That's why modern tank design focuses on preventing penetrations in the first place, rather than relying on crew escape procedures. Tanks also operate in nuclear, biological, and chemical environments. NBC protection systems create positive internal pressure by pumping filtered air into the crew compartment. This prevents contaminated air from entering through hatches, vision blocks, or ventilation systems. The crew can remain sealed inside for extended periods, though heat buildup and carbon dioxide accumulation eventually become limiting factors. Now let's talk about money. The M1 Abrams costs approximately $9 million per unit in current production. The German Leopard 2 costs around $7 million. The Russian T-90M costs roughly $4.5 million. These figures represent baseline configurations. Adding advanced optics, active protection systems, and upgraded armor packages can push costs significantly higher. This makes a tank not just equipment, but a high-value strategic asset. Beyond the purchase price, operators must budget for maintenance and fuel consumption. The M1 Abrams uses a gas turbine engine that consumes approximately 1.7 liters per kilometer in combat conditions. A single tank requires a logistics tail of 10 or more support vehicles carrying fuel, ammunition, and spare parts. Track segments wear out after roughly 3,000 kilometers. Engine rebuilds are required every 1,500 operating hours. Every component is expensive, heavy, and difficult to replace in the field. Regional design philosophies differ significantly. In the United States, tanks prioritize mobility and firepower using gas turbine engines for high power-to-weight ratios. In Russia, tanks emphasize mechanical simplicity and low unit cost with compact diesel engines and autoloaders that reduce crew size. In Germany, tanks focus on precision engineering and crew survivability, accepting higher costs for superior fire control and protection systems. There is no universal best design, only different solutions to the same problem. So, what comes next? The future of tank design is already taking shape. Unmanned turrets, like those on the Russian T-14 Armada, isolate the crew in an armored capsule separate from the gun and ammunition. Active protection systems such as Trophy and Iron Fist use radar to detect incoming projectiles and fire interceptors that destroy them before impact. AI-assisted fire control systems reduce engagement time from seconds to milliseconds. Tanks are beginning to coordinate with drones for reconnaissance and over-the-horizon targeting. Electric and hybrid powertrains are under development to reduce thermal signatures and improve fuel efficiency, though battery weight remains a significant engineering challenge. Despite these advances, the fundamental mission remains unchanged: control territory, survive direct attack, and deliver overwhelming firepower when required. And now, a simple question for you. What matters more for the future of armored warfare: maximizing crew protection through automation and standoff engagement, or preserving the ability to hold contested ground under direct fire?